Okay, so we are in this week here, projections bases. We're doing chapter 9 today, and which is about there's a chapter on bases, chapter 8, and there's a chapter on projections, which is chapter 9, and we're going to talk about it's the geometry of vectors that everything we've done with geometry has been qualitative. We haven't had any lengths of vectors, no areas, nothing perpendicular to anything else. And so we're going to sort of see how that works. And that sort of carries over to determinants. Both this chapter and this chapter are, both the projections and determinants are related to lengths. And then let's see. And also, let's see, what is, I don't know if I set, oh, yes, I think, let me make sure that I did that. I believe I set up, there was a desire to have let me see what is one. Yes, it's set up this afternoon. Oh, and I can change the due date here. No, it's okay. Oh, yes, I can change the Tuesday at this would be at 11:30. So if I add 12 to that, that would be 15. Okay. So demonstration 2.1, the second verse of demonstration will be available from this afternoon until like 11:30 or 12 noon on Tuesday, because you have class, because there's no classes on Monday because it's marathon day or tax day or whatever. So there's 3 days. So that's the second version of demonstration 2. And then next week, we'll have our last concept check at the end of a review. Whatever we don't finish today, we can continue with on Monday. But then we have a review of everything, nothing new here. And the following week, we start our last topics of determinants and spectral theory, which are eigenvectors and eigenvalues. Okay, so that's the sort of mechanics of what's going on. Also, there is a slightly revised revision 7 of the text, in which I cleaned up this chapter a little bit with some it's substantially the same, but it's just cleaned up with some typos, corrected some things, tried to make clearer. And but this is, I believe, chapter 9, which has to, the first thing is, the idea is, what do we mean by the length? We're going to give the idea of a length to a vector. Now, not all vector spaces, lengths and angles don't make sense to all vector spaces, right? I mean, if I have a polynomial vectors, I could define lengths, but that doesn't correspond to anything that makes any sense in terms of polynomial vectors. So this generally what we're thinking of is geometric vectors that are arrows in Euclidean space. So it's like we have, our vectors we can think of as arrows, or as having components. Like if this arrow could be in a plane, which is Euclidean, you think of the plane as having coordinates, but it's just a Euclidean plane, and we have components here, 2 column vectors, and we have arrows, and there's a connection between these two that we made in an earlier, when we first did the examples with vector spaces. We connected up this vector where we've established like an X and a Y lines, and then this distance here is X, and this distance here is a Y. So we have XY as a column vector where the X is up top, the Y down bottom. And so in this context, you can see that there's like with every vector, in the plane, you can ask, well, what's the length of this vector v here? And what's the angle between the horizontal, which you've chosen as a horizontal, and that vector? And we'd like to know that in terms of the components of R2, because we're saying that there's an isomorphism between these vectors here. You can think of them as in canonical position, right? And the components of these vectors. So and this is from the just the basic geometry. You know that what we're going to call the length of the vector, which is here the hypotenuse of this triangle, right? Is from Pythagoras' theorem, x squared plus y squared, where you're thinking of these x's as the length here and the length here. And this is just a result of geometry. You know, you can just go through and just use, you don't have to use coordinates. You can find that this length is related to this, to these two components like this. And this angle is, well, the simple way is sometimes you have these ratios, like the tangent of theta equals y over x, where we're assuming x is not equal to 0. And equivalently, that the cosine of the angle theta is going to be x over x squared plus y squared. This is sort of what you get from elementary geometry and how you specify angles via these trigonometric functions, which you think of as ratios, you know, which all tend to be ratio. You can think of them as you probably were introduced to these in terms of a unit circle when you had like a circle of length 1, and you thought of the angles as measuring, giving some measure. Anyway, the point is though that this is all based on Euclidean geometry. So the question is, what happens in r to the n and arrows in e to the n? Well, arrows in e to the n are just can sort of go through many dimensions, but then, and they have components in many coordinates. So I have a vector v that might have many components, x1, x2, xn, and the natural generalization of this formula is that just v equals the square root of x1 squared plus x2 squared plus dot 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 plus xn squared. And it turns out this makes sense. It's an algebraic generalization of this. And even though it's hard to visualize, you know, a vector in that space, you can think of it sort of like, okay, for each of these n coordinate axes, you could, it's sort of like there's like sort of like this could be the coordinate, the line for say x5, and this vector up here v is going to have a component, you know, along x5, right? And so you make this correspondence that this is going to be the length of this vector. So just generalized. So just you can't visualize it, but it's an algebraic generalization. And what the one immediate application is, you can see that all the standard basis vectors have length 1, right? Because only one of these will be non-zero, and its value will be 1, so that the length of it's just going to be 1. Okay. What about angles? Well, you need to use something called, to get the formula, in 2 dimensions, you use the law of cosines. You probably have forgotten that, but it's basically just an application of Pythagoras' theorem. And so if you do a little geometry, you take 2 triangles like this, and you say, here's side A, side B, and this is side C, but you divide it up into, there's a part X with triangle A and a part C minus X with triangle B. And then if you just apply Pythagoras' theorem to each of these two triangles, what you end up with is and this height here is H, say, so that you end up with A squared equals H squared plus X squared. That's this triangle. And then you do the same thing here, and you end up with B squared equals H squared plus C minus X squared. Okay, so and we're thinking about this angle theta in here, right? And so if I write this out, I've got B squared equals H squared plus C squared minus 2CX for the cross terms, plus X squared, right? And then I can see I've got X squared, I've got H squared, but that's just A. So B squared equals A squared, combining those two, plus C squared minus 2CX. Now, the question is, we want to trade in something here because we want to get this angle theta rather than C and X. So what you can see in this triangle here that the cosine of theta equals X over A, right? The adjacent side over this one, so that X equals A cosine theta. And so B squared equals A squared plus C squared minus 2 AC cosine theta. And this is the law of cosines. Okay, so the point of this algebra is just that you may be unfamiliar with the law of cosines here, but it's just the application of Pythagoras' theorem. Okay, that's all. Now, the problem is this only works for 2 dimensions. So the question is, what about higher dimensions, right? Well, because if you look here, so you've got the vector A here. You've got this protects as a vector here with C, and you have this one B here, which is opposite theta. So it's telling you a connection between the length opposite this and this angle. Okay. And let me show you where we are in the text. Oh, the wrong textbook. Okay. So here's this length formula. So here's the picture that you're at. You've got like a vector here, and the cross vector here. Well, that's what we want. What we've done with A, B, and C here, and this diagram, we're going to make into, I think if it is U minus V, I think this one is V and U, and this one is U minus V. Because you can see that if I want to add these two geometrically, I want to add V to whatever this is, I want to get U. Well, so if I add V and U minus V, the V's will cancel out and I'll get U. So that the difference of two vectors is the vector that points from the second one to the first one in the difference. Okay, so if I apply these lengths here, what I have is I have the length. This is like the B, this is like the A, and this is like the C. So I end up with this formula, U minus V, its length of this vector here, which is like B, equaling the length of V, which is A, plus the length of U, which is like C, minus 2 times the length of V, the length of U, times the cosine of the angle between the two vectors. Okay, so now if I write out, that's this formula here. If I write this out and do some algebra, I put in the components for all this, multiply it out. What I get is a formula for cosine theta equals V1 U1 plus V2 U2 plus V3 U3 over the magnitude of U times the magnitude of V. That's what's coming here. So if I multiply all these out, all the square terms cancel, and the only thing that survives is these cross terms. This is just the law of cosines written in vectors with 3 dimensions, right? There's nothing going on, but it's the point is we want to, this is the formula we can generalize to say the angle between any two vectors. Well, first of all, we want to give a general form. See, this is V1, V2, V3. We're going to define what's called the dot product between two vectors, say V and U. You punch it. V and U are, what I did was I started from this geometric diagram with A, B, and C, and then just said, well, let's put, this is V, the vector V here. This is the vector U here, and this is the vector here, U minus C, and that in our geometry, the length A is the length of V, C is the length of U, and B was the length of U minus C. So that allowed me to write down, this is the same formula where so this is the law of cosines, but written with the vector notation. Oh, V equals V1, V2, V3, and U equals U1, U2, U3. They're the components of V in 3 dimensions. And this is the components of V in 3 dimensions, the components of V in, I have like X, Y, and Z, or X1, X2, X3 components. And I have some vector V here that has components along all 3 axes. Is that what you were? Okay. So what I want to do is then generalize this formula. So we do that with first generalizing the numerator to say that the dot product of two vectors U and V in the same space is going to be V1 U1 plus V2 U2 plus Vn Un. Now this is very similar to matrix multiplication of like if I did V1 Vn and U1 Un, this is like the matrix multiplication of a row vector and a column vector. So the dot product comes from the notation comes from physics, where you were thinking of just 2 column vectors, and so you could write it as taking the transpose of the column vector and doing it matrix multiplication, but you don't have to. So we have the dot product of 2 vectors. So our generalized formula here is going to be the angle between 2 vectors in e to the n, or their analogs in r to the nc will be say v dot u over the magnitude of v times the magnitude of u. And now you're not guaranteed, because this is a generalization, you're not guaranteed right away by geometry that it makes sense. It could be that v dot u is larger than the denominator. So a priori, this is just an extension based on your expectation from geometry in 2 dimensions and 3 dimensions. Okay. So, but what you can do is you can go, here's the dot product, here's this formula that we expect to be the case, and we can write it everything in terms of the dot product, because the length of V squared equals V dot V. So the length of any vector equals the square root of V dot V, which means you can just, given components of a vector in R to the n, you can just algebraically compute V, U, and U dot V without having to do any geometry at all. That's the whole thing. And this is what you do in physics in 3 dimensions. You do some geometry of the physics of forces and velocities and other stuff, and then you do algebra to solve problems. Okay, but here, the point is there's some basic results. I'm not going to go over the proofs. They're here, that the shortest distance between, this is sort of like this inequality here holds, that U dot V is less than or equal to the lengths of these 2 vectors, U and V. So, because the whole point is these can add up and be straight together, or they could be an angle. But the point is the distance between the 2, as I change this angle, is going to always get smaller. And that leads to this equality here, which is the magnitude of U dot V is greater than this 2. It's called the Cauchy-Schwarz inequality. The value of this is, it's exactly what you need to show that this makes sense, this cosine theta. So this whole discussion here is just saying these 2 generalizations of length and angle to higher dimensions make sense algebraically or numerically. So, and they sort of make sense when you try to think about the geometry too. So we're just going to take that. Now, what's the point of all this? Well, we'd like to make bases where the basis vectors are perpendicular to each other. So we need notions of lengths and angles, and we need to know when 2 vectors are perpendicular. And if you notice up here, if you have this formula, well, if this is 90 degrees, the cosine of 90 degrees is 0. If you remember your, if I draw a vector here and here's theta, and here's x, right? So the cosine is this shadow here. So as theta goes to 90 degrees, the shadow goes to 0 length here, right? So the cosine of 90 degrees equals 0. So this is 0 exactly for vectors that aren't 0 themselves when the dot product is 0. So 2 vectors are perpendicular if U dot V equals 0. So that's our test. That's the whole point of this. We've got the lengths. We've got the condition for 2 vectors to be perpendicular. And if we want to make, we're getting to the place soon where you can do something with this, the first thing we have to, well, let's just do one exercise so you can, okay, so on page 476, number 1E, what is the length of 1 minus 1, 1, 0? This 4-dimensional vector, what's its length? So everyone has an answer? You have an answer, but I want to make sure everyone else does too. So you guys online all have answers?
Yeah, I have one.
Okay, so hopefully you all wrote down the square root of 3, right? Because 1 squared plus minus 1 squared plus 1 squared is square root of 3. Okay, so Oh, here's one. Let's see. Let's do number 4. Find K so that K1 and 4, 3 are perpendicular. Okay, and DiPancio has the answer before I can finish asking the question. Does everyone else have an answer? Will, I see you're speaking, but maybe not to us.
No, I was just groaning because I'm trying to think.
Okay. There's a lot of that in this course.
Yeah. uh,
So what you do is the condition of perpendicular is the dot product is 0. So you make the dot product of K1 dot 4, 3, which equals 4K plus 3. And these are perpendicular if this dot product equals 0, so that you can choose, if you choose K equals to minus 3/4, that will be true. That's all this is, right? Okay. I don't know why they have all these questions. Okay, I have to take some of those out. Okay, so now the section 2 of this chapter is a prelude to section 3, which is our target section, which has the procedure for given a basis, find basis of where all the of the same space, that where all the basis vectors are perpendicular. Like our basis vectors aren't, like for example, if we have, let's consider, we know this is a basis of R2, right? But these basis vectors equals 2 plus 2, which is not equal to 0, right? So these are not perpendicular. They're a basis, but they're not perpendicular. So basis vectors don't have to be perpendicular. They could be, like for example, these vectors, 1 times 1 plus minus 1 times plus 1 times minus 1 equals 1 minus 1 equals 0. So these are perpendicular. So you don't need to know the geometry to know if they're perpendicular. You just calculate the dot product. We want this, so for given this, we want to have a procedure to mechanically find a basis of the same space, which is where each vector is perpendicular to all the others. Okay, so what we need to do this is in the current section. It's called, we need to find something called the orthogonal projection onto a line. Okay, so here is the geometry here, in which we're given a vector V, and we have, say, a line L, and this line L is specified by, say, some direction S, okay? Now, if we want to find, let's say we want to find a vector that's in the direction of V, so to speak, but that's perpendicular to S. What that means is we want to go out to some point here and have a perpendicular line here, because we want a vector along this dotted line. That's our goal, right? So the problem is, if S doesn't point to this point here, we know that we could make it longer. We could make this length here be some number, this is like the point P, some number CP times S would go out to this point here, right? The length of this would equal the right length. We don't know what this is, right? But we know that there's some number that if I multiply S this S could be longer or shorter, we don't know. But there's some number CP that we want to find, because then this is what we mean. This is what we're going to mean. This length here is the projection of V on the line L, okay? So now the question here is, well, we've got this vector, and what's this vector here? Well, it's going to be V minus CPS, right? So this vector, because I start this CP times S goes all the way out to here. I add this to it, I get V. You see that? V equals V minus CPS plus CPS. That's all. We add this to this, that it works, okay? Now the question is, there's nothing here that fixes this point P, except for the fact that this vector is supposed to be perpendicular to the line L. But that means it's got to be perpendicular to the direction of S. So the condition that V minus CPS is perpendicular to S is that V minus CPS dot S equals 0, because then they're perpendicular. So then I can solve this for CP in terms of V and S, which is what I want. So I have V dot S. I'm assuming things like I can distribute this over CP S dot S equals 0. And you end up with the fact that CP equals, putting this on the side, V dot S over S dot S. And so this constant solves the problem of finding this distance here, this vector here, which is the orthogonal projection. So the projection, the squiggly line in that diagram is the orthogonal, the projection of V on the line S, which is the span of that thing. So what we want, the projection is, not program, projection equals V dot S over S dot S times S, because this is this constant, okay? This is what we want. This is what's going to be used in the next section. The whole point of this section is just to make sense of this, okay? There's some examples, and there's another way of looking at it, but let's, okay.
Professor, can I ask you a question?
Yes.
You cannot cancel out one vector S with the other of the denominator.
Excuse me?
You cannot cancel out the S's from the denominator and the...
No, because this is, okay, because this is a number.
Yeah, but that's not the same
This
number.
is a vector. This is a vector. I think what you're seeing is, and maybe what sort of is not so much you can't cancel out the numbers, but if I wrote S equals to some number S, which is the length, times the unit vector, where the length of S hat was equal to 1, then you're right, then I can cancel off the lengths. Then the projection here would equal V dot S hat over S hat dot S hat times S hat. And I've got two S's in the numerator and two S's in the denominator, and S hat dot S hat equals 1. So this is the same thing as V dot S hat times S hat, where, so, I mean, that is what you're seeing here. So there's a lot of S's, and what does get canceled out is the lengths of the vectors. So what it means is up here, if the projection, the magnitude of the projection V is entirely on how much of V is in this direction S, not in There's no, it doesn't matter how long the length of S factor cancels out, because that's just telling us how long the line is, right? You've seen this before if you've had physics. I think the work is equal to force dot dx, something like that. It's the component of force along the direction of displacement or something. Okay.
Yeah.
Just in case that makes sense to you. But we're not going to do that because we're going to be given S will be one of our basis vectors. So we're not going to go and normalize our basis vectors. We could normalize. Okay, I have used the word normalize. Normalize a vector means to divide by its magnitude, by its length, divide by length. So if I have V, its normalized form, which we could call V hat if we want, it's going to be V over the magnitude of V. And so the point is that the magnitude of V hat equals 1. If I write out the formulas, this works, right? So normalizing a vector means dividing it by its length, so it becomes length 1. And sometimes that's useful. Oftentimes, though, because this is a square root, it makes things really messy, right? So oftentimes we'll try to delay normalizing anything until the very end or never do it at all. Okay. So let's see. Here, let's on page 481. Let's do one of these intermediate exercises. Number 30. C. Find the if V is equal to 1, 1, 4, and S is equal to 1, 2, minus 1, find the projection of the first vector orthogonally onto the line spanned by the second vector. So it's telling you in these formulas up here that V is equal to 1, 1, 4, and S is equal to 1, 2, minus 1. So this is pointing off in some direction. It's pointing how much of V is on the direction of S. Okay, so calculate that. Calculate the projection of V on S. And again, Dipanshu seems to have an answer before I can even finish asking the question. I'll give everyone else time to try to find an answer. So either you're confident enough you can do it in your head, or you're so confused you can't get started. What? Well, you need either real paper or electronic paper or something, or you need the decision to wait until I give up on everyone answering the question and give you the answer anyway, right? After you do this exercise, then we'll go and go on to the last section, which is the one we actually want to practice with, which is the classical orthogonalization.
Professor, I got a question about the way you're notating the length. Is it supposed to be double lines or is it single lines to not confuse it with absolute value?
Single lines or double lines?
Like in the text for like the notation for length. Is it supposed to be single or double lines around
Go
the
back and look at the text and see what it does. These you can see them.
I think in this case it's the same.
Where do I have double lines?
see like how you have single lines there? I'm just curious if it
I have
is it
single lines here. Do I use double lines ever?
well, I'm just confused if isn't that supposed to represent absolute value? So what is there a way to
Oh, yes. Well, you're a programmer though. You know about polymorphism, right?
oh well yeah.
So this is a case of mathematical polymorphism in which you're using the same symbol depending on the
To take on a
content of what you're
different
putting into it. So if you put a
okay.
number between the bars, it's absolute value. If you put a vector, it's the length of the vector. If you
Oh,
later
all right.
on, if you put a determinant, it's going to be the magnitude, it's going to be the determinant. If you put a matrix between them, it'll be the determinant. So we're reusing, instead of having like separate symbols, we're reusing the same thing. And so
For different meanings.
yeah, and so you can remember it like you can remember it as a K. Now, mathematicians might say it's an abuse of notation and they'd want you to use double bars, but I think it's more insightful to use an analog, the three things by saying, okay, it's like, think of as as an exercise in polymorphism.
Yeah, makes sense when you say it like that. Yep.
I mean, if you weren't programmers, that wouldn't make any sense. But since most of you are like in computer
Well, at
science,
least object-oriented programming, but yeah, as far as that paradigm is
and you
concerned.
might not have heard, I mean, hopefully you've heard of some of you may or may not have heard of polymorphism. I don't know whether.
Well, yeah, definitely. I mean, at least it makes sense when you say it like that. At least I understand it. That's fine. All good. All right. Thank you.
If you use this and a mathematician accuses you of abusing the notation, you can just say, no, I'm engaging in polymorphism.
Even in calculus 3, we use the same thing.
Yeah, I think it's sometimes the problem is the danger is the more the notations also become very cluttered. If you use your symbols can interfere with it looks just like if you notice that the original text for matrices has the indices of matrices with a comma between them. And because like if I say M2, 3, well, it's really M2, 3. So the original author has commas everywhere. And I went through and took out all those commas out because it seems to me that it's much easier. Yeah, you have to realize this is not M23, this is M23. But if you learn to read that and look at some display with matrices like M T1, T2, having the extra comma just makes it visually cluttered. Because if you have like a 3x3 matrix, you've got like 9 commas, and it just sort of, I like the cleanness, anyway, but it's like a aesthetic kind of issue or whatever.
Do you want the result for the?
Okay, so let's see. Okay, so well, let me do it. You guys have had time to do it, so we see.
Professor, I think there's an answer in the chat.
Oh, okay. Okay, so so one person is saying, I presume that the vector is -1/6, -1/3, -1/6. Okay. Well, let's see if
It should be positive 1/6 at the third component, but they were close.
Positive. Okay, let's go through and do that. 1, 2, -1. That's the dot product there. Then this is 1, 2, -1. Dot 1, 2, -1 times 1, 2, -1, right?
Yeah.
And then this is going to equal, well, this is going to be 1 plus 2 plus -2. -4 will be -2 in the numerator, right? And this one will be 1, excuse me? Oh, yeah, because it's 3, so it's -1. Okay, -1. And then this is going to be 1 plus 4 is 5, plus 1 is 6, times 1, 2, minus 1. And so you could, and then that, if you left this alone or multiplied in, you're going to get minus 1/6, minus say 2/6, and plus 1/6. Sometimes it's easier to leave this like this rather than reducing. These are the same. This is correct. Okay, so that is finding the orthogonal projection. This is the vector that shows you how much of this vector is lying along this line here. Well, that is what we need from this section here, the orthogonal projection. And there's some examples, right? And you do exercises. And then we come to so for this chapter, what you have to do is find lengths of vectors, find angles between vectors, find orthogonal projections, and then given a basis, find orthogonal basis. And those tasks are it for this chapter, okay? So let's say that we have a basis beta 1, beta 2, and let's say that beta 1, beta 2 is not orthogonal. What we want to find is kappa 1, kappa 2, such that kappa 1 dot kappa 2 equals 0. Okay, so here's the procedure. It's the classical procedure to do this. This early mathematician Laplace knew about this procedure in the early 1800s, and then it was developed by Graham and Schmidt, so it's sometimes called the Graham-Schmidt orthogonalization procedure. But so we're going to de-emphasize Schmidt because he was a Nazi in World War II, called the classical orthogonalization procedure. Okay, but if you hear, otherwise we refer to as the Graham-Schmidt orthogonalization procedure. Okay, so this procedure is, what would you do is this: you take kappa 1 to be beta 1. Okay, you just take the first one, make it identical. Then kappa 2 is going to equal, you start with beta 2 and subtract off the projection of kappa 2 on kappa 1, because you want kappa 2 to be perpendicular to kappa 1. Now it is beta 1, but we're going to leave it as kappa 1. So you want kappa 2 times kappa 1. So kappa 2 is your v. You want to subtract off the projection of v on the earlier one. We're using kappas because they're sort of like, kappa sounds more orthogonal because they've got more edges, I suppose, than right. There's the formula, right?
But it's not gonna be over kappa 1 times kappa 1. It's gonna be kappa 1 times
Yes,
kappa
right.
2.
Kappa 1 times kappa 1. Okay, so try this out. Let's say that basis B equals 1, 1, 1, 0. Okay. So what basis does this procedure produce? So you want to, given B, this is your beta 1, this is your beta 2. What is kappa 1 and kappa 2? What is your orthogonal basis K? Well, okay. kappa 1 is beta 1, right? You know beta 1 and beta 2. Kappa 2 is beta 2. Kappa 2 dot kappa 1, which you know from this. What?
But we don't know kappa 2 yet, and how are we gonna find the?
Oh, yes. Sorry about that. Oh, no. Let me see. Yes. Okay. So, yes. Okay. Sorry about that. You're absolutely right. We don't know kappa 2, right? So, oh, in fact, actually, the point is, what do I have here? Yes. I completely messed it up, right?
So it should be beta.
We want the projection of beta 2 on kappa 1, right? So that's the only, this, otherwise it'd be completely circular, right? Have an infinite regress. In fact,
Professor,
actually, it would it would actually always, it would almost always be a logical contradiction.
do you need an answer for that?
Do you have an answer? Oh, so someone has an answer. Okay, so why don't you? You want to tell me an answer?
It's -1, -2. Maybe.
So this one is 1, 1, right?
Yes.
I
And the
got
th-
1/2, 1/2.
What's the second one? One
One
half.
half.
And I
Yeah.
found -1, -2. Well, maybe it's
I think
wrong.
So what
I
is the
think it-
second one?
Go ahead, go on.
Go with Zakari first.
I got 1/2, 1/2 for the vector components
Of the second one?
of the second one for K2, yes.
1/2? 1/2?
1/2, 1/2 for the vector components X and Y, yep.
Well, that can't possibly be the case because the dot product of these is not 0.
So
Right.
yeah, the dot product of the two vectors in the top ended up being
Wait,
one.
this
Mhm.
cannot be kappa 1 and kappa 2, right? This has to
So-
be 0, so you've done something wrong. So this is not, can't possibly be correct, right?
All right, I'll wait to see the right answer then. I think
Uh,
Does someone else have an
Can
answer?
you try -1, -2?
-1, -2?
Yeah.
Well, that would be the dot product would be -1 plus -2, which is also not 0.
Okay.
Okay, so someone want to try again?
I made a mistake. I forgot to take the difference. So I will, yeah, I forgot, yeah, because K2 is supposed to be, so 1, 0 minus 1/2, 1/2. That was my bad. So now that answer should be the right vector when you take the product.
What components do you want me to put here?
So the first thing I just forgot to take the difference for K2. So K2, it should have been the vector 1, 0 minus the vector 1/2, 1/2. And that vector itself, the product of that vector with
So
the
what
vector
is your final
1.
answer?
Oh, okay. All right. Well, I'll get back to you.
Okay. Does anyone else have? Yeah, Deepanshu, I haven't let you because I know you're so quick. You've been penalized. So what is your answer, Deepanshu? Is that right? Okay,
I can see the dot product is.
okay. Does anyone else
So-
want to take a stab at it?
So should be.
Will.
negative.
You want to say it's 1, -1?
That's what it.
It should be.
But that's the only way it's gonna be, 0. So it should be.
Well, yeah, but the point is not what it should be. I mean, we can think of lots of bases for, it's not what it should be, because we can think of, like, for example, if I put 1, 2 here, that's also 1, 2, well, yeah, you can also figure out other, like 1/2 minus 1/2, 1/3 minus 1/3, maybe.
Are you sure that, what we are dividing by is beta, is kappa 1 and beta?
Yes, because look, well, okay, let's look and see in down here, right? Let's see. Yeah, look. Oh, I don't write it out exactly there. Let's see. It's the projection of K. See, it's the projection of K1 on beta. It's the projection of beta 2 on the span of K1. So it is the projection of beta 2 on K, because we want to we have beta 2, but we know it's not perpendicular to beta 1.
So the solution,
You want
so
to
the solution-
subtract. Well, let's see if I just take, this should work for any vectors, right? If I take kappa 1 dot kappa 2, I shouldn't have to put in particular vectors. It has to work for everything. So it has to work. So let's write this out. Well, it's going to be beta 1 dot beta 2 minus beta 2 dot beta 2, beta 1 over beta 1 dot beta 1 times beta 1, right? This was,
But why you have a beta 2 at the beginning also?
oh, well, I need
Gotta take the
I need
difference.
this to be 0. I want this to be 0, right? So kappa 1 is beta 1, and I want beta 2 minus beta 2, and kappa 1 is beta 1. So it's beta 1 over, oh, I'm going uphill. Let me rewrite this so it doesn't slope upwards. Because I want this formula here to check it with beta 2. The kappa 1 is beta 1. So I'm going to do beta 1 dot beta 1 times beta 1, right?
Yeah.
Okay. And let's see if I've made a mistake. Beta 1 dot beta 2 minus, I'm going to copy this, beta 2 dot beta 1 over beta 1 dot beta 1. I just copied this, but I have beta 1 dot beta 1. Okay, well, this is beta 1 dot beta 1 in the denominator, beta 1 dot beta 1 in the numerator. That cancels that, and I have beta 1 dot beta 2 minus beta 2 dot beta 1, which equals 0 in all cases. So this formula works. But let me go
I
through.
noticed, Professor, when I took the difference instead, I still got 1/2 and -1/2. So I'd like
That's
to
what
see.
I got too.
Yeah, so how do you do it? Is like, because I don't,
Okay, well, let's go through and see.
I don't know anymore.
And we'll see what happens. Okay, so we have B equals 1, 1, 1, 0, right?
Yeah.
Those are the two I chose, right?
That's correct.
Okay. Somewhere, oh, there they are. Yeah. Okay, so we take kappa 1 equal to 1, 1. We all agree on that, right?
Yeah.
You have no choice there. Okay, well, this one should be 1, 0 minus, and then 1, 0 dot 1, 1 over 1, 1 dot 1, 1 times 1, 1.
Yes.
Yeah.
Okay, so this should equal 1, 0 minus, and this is going to be a 1
1/2.
here, right?
1/2.
No, 1, okay, yeah, then this is going to be a 1/2, and then times 1, 1,
Yep.
and then I'm going to have 1/2 up here, and minus 1/2 down here. 0 minus 1 minus.
Yeah, that's what we got.
Okay, and then you can do kappa 1, check it with kappa 1, kappa 2 equals 1, 1 dot 1 half minus 1/2
Equals 0.
And it's not 0.
minus 1/2, which equals 0. So it's perpendicular.
What? 1 times 1.
1 times 1/2.
Oh,
is
I meant I didn't. I was just doing 1 times 1/2, 1 times -1. You meant the dot product of the whole, like, so 1 times 1/2 plus 1 times
plus
-1/2,
1
which is 1/2 minus 1.
equals 0.
Never mind. Okay, all good.
Okay,
Yeah,
so what happens if we have B equals to beta 1, beta 2, and beta 3? And we would need to find the basis kappa 1. I'll try to be more precise in my writing. Kappa 3, right? Where we need kappa 1 dot kappa 2 equals 0, and kappa 1 dot kappa 3 is 0, and kappa 2 dot kappa 3, if they all have to be perpendicular to each other? Well, we start the same way. Kappa 1 equals beta 1. And kappa 2 equals beta 2 minus beta 2 dot kappa 1 over kappa 1 dot kappa 1 times kappa 1. That's the same thing as before, right?
Yeah.
So that each formula for the next one is just going to have the previous formulas inside it. So for example, the patterns here is going to be so that once we get kappa 3, you'll see how everything works, because you'll see what we do to get from here to here is the same thing you do from K3 to K4.
So what you gonna do? B3 times kappa 2.
Yeah, well, we'll get there. Yeah, there's a question in class. Yeah, so we need all the kappas to be perpendicular. But we've got so far is that just kappa 1 and kappa 2 are perpendicular. Well, this is the same formula as before. So we know at this point that kappa 1 equals kappa 2 equals 0, right? Okay, but we have to find kappa 3. Well, kappa 3 is going to be beta 3 minus beta 3 dot kappa 1 over kappa 1 dot kappa 1 times kappa 1. You subtract off the part of beta 3 that's perpendicular to kappa 1, and you also subtract off the part
Kappa 2.
3 that's along the direction of kappa 2. Right? And so what's going to happen is then, if I multiply beta 1 in here, I'm going to have products of beta 1 and beta 3, and this beta 1 and beta 3. It's annoying with, if I want to check that kappa 2 is perpendicular to kappa 3, you can see the problem is going to be that I can do that, but then when I multiply this out, I can put in for kappa 1, beta 1, but for kappa 2, I have to put in this whole thing here. So the algebra is tedious, right? So, but it's true. But if you check it, I mean, that's what those guys figured out, that this always works. And then if you figure out for the case of n, you need to use what's called a proof by induction, where you show that if it works for the first n cases, it's going to work for the next case. And then there's an induction theorem that tells you that, oh, if you know it works for the first case, and if you know if it works for the nth case, it also works for the n minus n plus 1 case, then it's going to work. There can't be one where it doesn't work. So there's a principle that you can get out these, but obviously you can go, if you did kappa, if it was a 4, you'd have kappa 4 was beta 4, and you'd subtract and you do beta 4 on kappa 1 and beta 4 on kappa 2 and beta 4 on kappa 3, and you would then go crazy if you do that. So the point is then that let's practice this with, let's say that B equals 1, 0, 1, 1, 1, 0, and 0, 1, 1. And none of them are perpendicular to any of the other ones. Okay, here's beta 1, beta 2, beta 3, and what does the classical procedure produce for kappa 1, kappa 2, and kappa 3? Excuse me?
Store the block of-
Oh. Yeah, there. Sorry about that.
Can we verify what is K2 so we don't do operations for no reason?
Okay, yeah, so I'll do, so kappa 1 equals 101, right?
Yes.
And kappa 2 is going to equal
Do you want an answer for that?
beta 2. Let me just,
Oh,
then you can see, minus 110.101, right? Over 101.101 times 101, which equals 110 minus 1 half, right? Times 101. So hopefully you got for kappa 2, 1 minus a half is 1 half. 1 is 1 half minus 0, and
negative 1/2.
minus 1 half. And you can verify that it is perpendicular to kappa 1 because it's the dot product is 1 half plus 0 plus minus 1 half. So that works. So is this what you guys got for kappa 2?
Yeah.
Okay, now that you're assured that you're not spinning your wheels, you can go and find kappa 3. I'll give an answer.
No yet.
Okay, we'll take Phoenix. What is your answer? Okay, well, let's see. This would be minus 1/2. If I do the dot product of this and this, what? Minus 1/2 0. It looks like something is wrong. Okay, you got, so this doesn't quite work, okay? Mine, you have 1/2 and minus 1/2? What? Positive 1/2. Okay, so this would be minus 1/2 plus 1/2 would be 0, and then minus 1/4. That doesn't work.
Is the first one -4/6?
The first, what do you mean the first one?
Um,
I don't know the answer.
the first row. No, I'm just letting you know because like that's what I do right
think the
now.
first- You think the first entry, the first component
The
here
first entry, yes.
is what?
-4/6, like -2/3.
Minus 4/6?
Yeah.
Well, okay, oh, well, I don't know the answer, so I don't, so that only if we have all three components, is it good, can we say anything? Zach,
All right. So -4/6, 2/3.
well, you have -4/6. Then what?
2/3,
2/3,
and the last one I have 3/6, 6. 2/6, which is 1/3.
2/6, okay. Well, let's see. This would be minus 1/6.
I got something.
Okay, let me just see if this works. Minus 1/6 plus 4/6 is plus 3/6. 3/6. What was this?
1/3.
I don't know what I wrote.
2/6.
The last one was 1/3.
Yeah.
One was let me see, minus 1/2 plus 4/6 is 1/2, and this is minus 1/6. So that wouldn't work.
That won't work.
So that would, it would, I think it would, well, if I think unless I did my arithmetic wrong. Zach, did you have an answer?
Yeah, so well, looks like so the first and the second vector were established, but the third vector I got -2/3, 2/3, and 2/3.
-2/3, 2/3, and 2/3, right?
But yes, that it appears to be.
This would be, if doing the dot product of these two would be minus 1/3 plus 1/3, right? This would be minus 1/3 plus
When-
2/3 is plus 1/3 minus 1/3, so that would work.
Okay. Well, the dot product is so when it's more than two vectors, you just do it the same idea, like it'd be 1 times 1/2 times -2/3 plus 0 times 1.
Would be 1/2 times minus 2/3 plus 1 times 2/3 plus minus 1/2 times 2/3, and that does indeed.
Oh, so you would just make sure that you would do it by two vectors at a time, so the first and the second and the second and the third, or no?
Well, I would also, if I wanted to check, make sure that the first one, 1/0/1, so this would also work with one, because I had minus 1/2 plus 2/3 is 0. Okay, so let's see if how one would do that, right? So let me see, what was the third one? You would have 0/1/1 minus 0/1/1 times 1/0/1 over 1/0/1.1/0/1 times 1/0/1 minus 0/1/1, this vector, dot kappa 2, right?
Yeah.
Which is 1/2 1 minus 1/2 over 1/2 1 minus 1/2 times 1/2 1 minus 1/2 times 1/2 1 minus 1/2. Right? So that if that's right, that would be 0, 1, 1 minus, and this is 1 over,
1/2.
yes, that's a 0 there. 1/2 over 2 times 1, 0, 1 minus, and this would be 1
1/2.
minus 1/2 is 1/2 in the numerator, right?
3/2.
And then this is 1/4 plus 1 plus 1/4, right?
Yeah.
Times 1/2 1 minus 1/2, which equals, doing this first one will be minus 1/2 1/2 I think, minus 1/2. Oh no, minus 1/2 1 1/2, because this just gives this, well, I'm not sure what that, okay, so it's minus, and this is 1 plus 1/2 is 3/2, so that's 1/3 over 1/2 1 minus 1/2, which equals, it looks like minus 3/6 minus 1/6 is minus 4/6,
Oh, that's a minus.
which equals minus 2/3. This is what Dimitri said, which is correct, and then it just reduced. Then this would be 1/2 minus 1/3 is 2/3, and the last one is 3/6 plus 1/6 is 4/6, which equals 2/3. Which was similar, which is, I think, isn't that what you guys got?
Yeah, instead I only had the third component. I instead of having 2/3, I had 1/3.
Oh, I erased Zach's answer. This
Yeah, see, I only gave that one, but I gave it in the most simplified possible form. That's just, I
and,
just,
yeah, Dimitri, I think you had you were missing one of these fractions.
I missed one fraction, the bottom one. Instead of having 2/3, I had 1/3.
Okay. So you can see that the smart thing to do is do this on a computer, right? And
What do you mean?
you can, I mean, you could do that, you could, if you had you have to have a dot product thing, but if you did this, it's obviously, that's one of the advantages of it. And so here is the general, see, it's written out as the project, like K3 is beta 3, the projection of beta 3 on K1 minus the projection of beta 3 on K2, and it just you just keep going, right? So that's the procedure. And all that there's nothing, there's nothing more to it except, and obviously we're not going to do a basis with 4 vectors. Okay. So, and normalization, you can take a vector, and an orthonormal basis is one that the vectors are orthogonal and unit length. So if you got an orthonormal basis, then the vectors would all be length 1 and they'd all be perpendicular.
so how can you check for that, Professor? Like once you get the orthonormal basis, how can you know if you've done it correctly? Is there a way to see if it's equal to 1 somehow?
Like if this was orthonormal basis here, you'd have to take the magnitude of each vector, see that it was 1, right? Here, because you'd see this was 1/3 plus 1/3 plus 1/3. This would be 1/6 plus 2/6 plus 1/6. Well, it'd be 1/6 plus 4/6 plus 1/6 would be would be 6, 6, would be 1, and then this would be 1/2 plus 1/2. So they're all normalized. And then you'd have to do the first one dot the second one, the first one dot the third one, and the second one dot the third one. There's no easy check. I mean, you just have to check everything.
Okay.
And that is it for this chapter, right? Let's look and see what you need to practice with for assignment 6, which is your next to last assignment. So here is 2 vectors in R5 in 5-dimensional space. What is the length of each vector? What's the dot product? I don't know how to make a giant dot. It's the giant dot product, right? You can either use a C dot or you can use a bullet. And this is like a bullet. So that there's, anyway. What's the dot product? What's the cosine of the angle between the 2 vectors? Okay. Here is find the orthogonal projection of V on the line spanned by W. This means find the component of V along the line of W. Okay, here's a basis for R2. Use the standard orthogonalization procedure explicitly to find an orthogonal basis. Normalize the vectors as orthogonal basis and so provide an orthonormal basis for R2. Here's the basis for R3. Use the standard procedure to find the orthogonal basis. This is what we've just done, right? It's just done one more case and being careful about it and presenting your results in reasonable fashion and using complete sentences. Okay, then this is the stuff that goes back to the last chapters, that the order of the problems is inverted, right? This is consider the implementation of a linear map from P2 to P2 via the following matrix G, acting on the vectors in the standard basis for both domain and codomain. A, use the matrix action on the representation of a general vector to find the general polynomial form of the map. So you'll have polynomial goes to polynomial. Okay, find the inverse, G inverse of G, using explicitly the giant augmented matrix method. C, find the general form of the inverse map, G inverse to G. That's going to be polynomials to polynomials by using the action of G inverse on a general vector of the codomain. Okay, so basically I'm asking you, given this matrix, what's the polynomial form of the map of G? And then, because it's 1-to-1 and onto, what's the inverse polynomial map? But you get it from using the matrix representations rather than messing with some algebra. So 6 is a little bit more involved. 7, again, here's another map from P2 to P2, but I'm giving the explicit formula and says what matrix H1 represents this map on the standard basis. Follow the standard procedure using only column vectors as representations of a particular basis, not in place of the polynomial vectors. So for example, when I find the images, the basis vectors, I find the images, the basis vectors with this map polynomial to polynomial, and then go in the codomain and find the representations of the matrix. B, what is the matrix which represents the same map using this basis? Okay. So then you'll have to find the images of the basis vectors and find under this same map, but then take the representation of these vectors in this unusual basis. Okay, then 8A, this goes to the section on identity maps. Find the matrix, the matrix IEB, which implements the identity map on R3, sending a vector in basis E to the same vector in this basis. Find the other way, which goes from B to back to the standard basis. What's the product? Find the vector IBB, which implements the identity map on any 2-dimensional vector space. It sends a vector in basis B from V2 to the same vector in the same basis. Then here's this one with you have to find everything. It says check the identity, this identity in two ways, as described in parts A and B. Here, JEE is the representation of the map J in the standard basis to standard basis. This is the identity matrix, which takes you vectors in R2 to this basis, and this I3 ED takes you from is the representation of the identity on this basis. So then you can calculate this product and then multiply them together, and you get the representation of JBD. So you're given a representation of a map in the standard bases, and you're asked to find the representation of the map in B and D by going through this procedure where you're using basis transformations, which are representations of the identity. So you don't actually have to understand I've tried to lay out so you don't have to understand everything, the meaning of what's everything. If you can follow the directions and do everything, it should just work out. Okay, that's it for these problems, which I think are due like next Monday night, right? This is the first week, the second week. So you want to work on, so these was the one, so what you want to do is work on these. Like, for example, one strategy would be work the first 5, which are like in one category, right? Then work the second 5, because those are the ones that are more conceptually messy. Or may give you, you have to have polynomials or whatever like that. Okay, so that is where we are with that. And you have and then the next chapter, we start with determinants, which I've forbidden you to use before chapter 10, right? Like the problem has been that you yes. So anyway, so
What are the determinants?
excuse me?
What are the determinants?
A determinant is a map from a matrix to a number that detects singularity. It detects whether a map is singular or not. And the determinant, so it's a number, and we get that number with Gauss's method. So basically, it's going to be an exercise in applying. But the chapter is trying to introduce you to what the meaning of determinants. Like there's these weird formulas, if you've seen them before. We've seen them sometimes before with weird formulas, right? But the question is, where do those weird formulas come from, and what are they doing? Because they look just nonsensical. They don't look like they're connected to what they're supposed to be connected to. And even if and also if the determinant's 5 versus 10, what does that mean?
But why did you say that you forbade us from using it even if we didn't?
Because some
How
people,
can we use that if we don't?
people, I would ask you whether a linear system was singular or not. And some people would calculate the determinant of the matrix from the linear system and say, well, it's not 0, so it's not singular, or it's 0 or it's singular. And that avoids that's what you might get from looking online or having previous information. And it's true, but it's not, but we don't know anything about determinants formally, and that it avoids exhibiting. What I wanted to know was, do you understand that a singular matrix is a matrix of a homogeneous linear system that has an infinite number of solutions, and that a non-singular matrix is a matrix which has
No solution.
is the coefficient matrix of a homogeneous linear system with exactly one solution. So the point was to use that definition and to go through and say, okay, look, here's the matrix. We reduce it to echelon form, has a free variable, therefore has an infinite number of solutions, therefore it's singular. So the idea was, have you followed the definition of singular and non-singular? Because then we come to determinants, we want to derive the idea of a determinant from that definition. And then we're going to find out that yes, if a determinant is 0, the matrix is singular. And if it's not zero, it's not singular. So,
Professor, I just wanted to double check on when the assignment 5 version 2 and assignment 6 are due. Are you saying they're due Marathon Monday?
I hope not.
Oh, okay. Thank God.
Well, let me check and see. Oh, we are here. Assignment 6 is due on is due.
Oh, okay, 2 weeks. Got it.
3rd. So here we are. You know, you've got you've got this week, but we now have sort of begun to see all the material. So you have this week and this weekend, and then it's going to be due on Monday night on the 23rd.
Yep. Okay, thank you. I just wanted to double check to I misheard you and I thought it was due next week, so thank you.
Right, it's not. And then I think this last one is due on well, the issue here is I think that I think our last day of class is on May 10th. Right?
And then it's finals week, right?
Right, but there's no final in this course. There's just
Yeah, it's the demonstration and
the
concept
last
checks.
class is May 10th. So your last homework is due on that Sunday night before finals week. But the last assignment deals with determinants and eigenvectors and eigenvalues. It's actually relatively smaller than the other ones. So any other questions? Let's, oh, I have an idea. Maybe this would help. Let's look at a map Q from x minus b x squared, right? And let's say that we had basis b equaling 1 plus x, 1 minus x, and we have basis c equaling x squared 1x. Okay, what is Q B C? Oh, you could also ask. Oh, well, we could ask. We could also ask, what is Q E E? Right. And what is I from EB? Or maybe B E and then E D. So you could calculate QBC equals IBE QEE and IEC. There's no D. So you could calculate this directly, right? But you could calculate it this way. So this is method option. This is option B.
And the E stands for the identity matrix, or
Oh, well, there's two E's. One E for the first space, E would be 1x. For the second space, E would equal 1x squared. I don't know if there's time to for you to finish all that in 10 minutes, but so probably we should why don't you start it or see if you what conceptual, see if you can get started and then ask questions about it, and then we can continue with it on Monday. Well, I guess we won't continue with it on Monday. We'll continue with it on Wednesday. Because maybe because next week we have a short week, right? But then I think the following week we have a review week or something like that. So yes, next week on the 15th is a review week, so we don't start determinants next week. So we can continue with this on Wednesday, and then also maybe on next Friday also we can have time to work on some, spend a little more extensive time, say, working on the assignment, because you probably have other courses where you're getting busy with other stuff at the end of the semester. Zach, you had a question?
Yeah, so I was just curious if, since there's just not enough time really to get this, is it possible to try to say out conceptually what I think might be going on?
Well, if what they're so we don't end up with the question is if you can isolate one idea. Yes, I know that. Good luck, Tyler. I know that there's. Hopefully we can spend some more time in class, so you get uncrushed or whatever. Zach, so if you can isolate one problem instead of trying to say the whole thing at once, what particular?
Can I at least try to see about where to start?
Yes,
I guess.
Tell me, but just not like with a huge thing. The question is, which quantity do you like? You can calculate any one of these, right? Which one do you want to start with?
So I don't think I'm fully understanding how to get those matrix quantities, but I think I'm understanding how to try to get it started to transfer.
So which one, if any of them?
I guess the matrix Q, which maps the standard basis to the standard basis.
Well, okay, so that how is a matrix, because you have a map, right? And Q is the matrix representation of the map. So you have to think, what's the definition of the matrix that represents a map? There's there's like a basic definition. You have to have that definition in mind.
So I guess would I start by taking the standard basis that's of polynomials of the quadratic polynomials and trying to run it through the function, and then that column 1, 2, and
The definition of G.
You'd start from the standard basis on the domain and find the images of the domain basis vectors with the map.
so looking at the
Then-
domain, you would have the
Then you would write that each of those images as a column vector,
yeah, and then that would represent
Standard
the
basis.
map.
and those columns would be the columns of QE, right?
So did you already get the basis that like the vector, the polynomial vectors in the domain is the basis for them, one of those two bases at the bottom there?
The basis here, it's the standard basis for P2 is 1x.
Okay, so I'm just so to understand that taking those vectors and running them through the function, that itself will create the columns for the
Yeah.
map Q that would represent the standard basis to the standard basis linear transformation.
You take the image of 1 and the image of x through this formula. You'll get answers for each one of them as polynomials. Then you would write each of those polynomials as a column vector.
Yep.
Using this basis.
So you would see what those would look like expressed in terms of that basis.
Column vectors would be the columns of your matrix. You'd have QEE.
Okay, which maps from, so to understand, it's the mapping of the standard basis of the domain to the standard basis of the codomain. They have two different standard bases, it looks like, represented by those two bases.
There's like, formally they're E2 and E3 because
Okay,
this
that helps, that helps.
E2 and P, or P, rather P1. Or maybe we could call this E standard basis 1 and standard basis 2, because this is
Yeah, they wouldn't be the same. It wouldn't be like EE, it wouldn't be the same standard basis then.
like 2 because it's P. So I say we have space P2 with standard basis E2, right? And P1 with standard basis E1. So you'd find this just using the standard bases, right?
You take the images and then see what those images look like with respect to the second basis, and then those scalars would be the new, that would be
The matrix.
that
Represent-
that would create the column vectors that would represent the map for Q that maps from E to E, standard basis to standard basis.
right.
Okay, so at least that part, so I can
Would
try
have
to sense of the, so it sounds like the process would be very similar to find the identity map, which maps B to E. You would take the base, the vectors in the basis, the general basis B, and just find their images, and then take those images and see what those look like with respect to the standard basis E, which is the standard
those
basis to the codomain.
columns of this matrix.
And then that'll be column vectors to create the matrix of IBE, and then do that process the same way with IEC, and then take the product of all three of them to get QBC.
Going to be E1, and this will be E2. This will be the images of these things, right?
All right, so it's very, sounds like it's very similar to the 10th problem in assignment 6. It's like similar to that sort of idea.
It's exactly the same as
That helps. Okay. All good. That's very clear. That's all. Thank you.
And once you find this, you find the two identity maps, then you multiply them together as matrices.
And that matrix result itself is the mapping from B, the general basis B to the general basis C in terms of basis B for the domain and basis C for the codomain.
And you could check that by saying, well, this matrix, by take a vector in P1, write it in basis B, or you could take a vector in P1 and find what the output is, right?
So a vector in P1 that is explicitly in the basis B, that itself, if you were to take the multiplication of that column vector with the matrix here, that will give you a representational vector that can be represented in the basis C of the codomain.
Well, this one will give you it in basis C, and then you could you could rewrite that and compare it to this. So you could compare, see, does this work the way it's supposed to work?
Okay. That'd be a way to like try to see if it works. So a way to see if you got the right, like to see if you did everything correctly, you could take a vector that was like say 1 plus X in standard base in general basis B, and you can run it through, you can multiply that column vector with the matrix QBC that maps B to C, and then see if you get this a vector in C that would be expressed as P2, like P1 to P2.
Sort of like you're starting from you're starting to sort of P1 and going with Q to P2, right? And then the alternative is you go
This matrix itself is supposed to shortcut all of that though, right? So that's what it's supposed to do, is take it and transfer it to the basis in P2, the general base, that general basis in P2.
yeah. So because you want here, you want to start with a VB here, right? And go IBE to P1, and then come across here with QEE, right? And then get this in P2 with, here you have E2, and then you come back here with IEC, right? So the point is, you're constructing this by matrix multiplication. That's what this is. But
The
you
matrix multiplication, that's what's shortcutting doing all of those steps in one product. It's like taking the product and doing all of those steps.
so this is sort of the worst kind of, I mean, it's the most involved kind of problem, right?
It seems to be. Okay. All right. Good. Thank you.
Everything else after this in the course is more algorithmic. It's like the eigenvectors and eigenvectors are more like the orthogonalization. They're doing stuff. Well, it's 1:49. Any 60-second questions?
When will this recording be on Piazza?
Oh, let me stop it. So I will not record when I will put the recording up